All right, 3.8 is about factoring special polynomials. So we're going to take a look at some special polynomials, and we are going to start by expanding each of these. And I think that if you want to copy this down, you can. You should know how to do this. So I would like to do this just real quick, and we're going to try and notice some patterns here. All right, and we'll see what the patterns are when we expand a binomial times itself. So the squared really means times itself. So when you see a squared like that, for this first one, it really means x plus 1 times x plus 1, right? And so that answer, if we expand that out, is going to be x squared plus 2x plus 1. Agreed? This one's going to be x squared minus 2x plus 1. Because if I change those signs here and I distribute, I have negative x, so negative 2x. And negative times a negative is still a positive when you multiply. This one here is going to be 4x squared plus 4x plus 1. This one's going to be 4x, and if you can't do this in your head like I'm doing it, don't worry about it. Okay, if you have to write it out and do FOIL, that's totally fine. It's totally fine. I'm just doing this quick so that we can see the patterns is what we're trying to get to, okay? So 4x squared minus 4x plus 1. This one is going to be x squared plus, anybody know? Just offhand, shout it out. You want to shout it out? I want to give it a try?
Plus 4x.
Plus 4x plus 4. Okay, some of you are recognizing the pattern here. X squared minus 4x plus 4. Okay. 9x squared plus 3x times 1 times 2. That's what we've been doing. So that's 6x plus 1. This one's going to be 9x squared minus 6x plus 1. All right. So what we want to do is we want to notice some patterns here. We want to notice some patterns, and we've already started to notice the patterns there at the very end. But notice that the first term, whatever it is, the first term, when you expand this, always gives you a term that's squared. That's that term squared, okay? It makes sense if this is a squared thing. So the first term is always squared. And look at this. The last term is always squared here as well. So let's move over here. 2 squared is 4. Negative 2 squared is 4. So the last term in the binomial and the last term in the product trinomial are related that way. So we got the first term is the first term squared, and the last term is the last term squared. The middle term now, and we just were talking about this. Whoops, I'm erasing too much. We were just talking about this, but the middle term is going to be this term times 2. So 2 times 2x, that's what this is. This term times 2. So 2 times 3x is here. This term times 2. That's negative 3x times 2, negative 6x. So this is the pattern, a plus b squared. You want to write this down? So a can be anything, b can be anything, positive, negative, you know, as long as it's a single term. You can have numbers, letters, whatever, 3x squared or 3ab, x, y, z squared, whatever. As long as it's a single term. What we end up with is when we expand this, we end up with a squared at the beginning. We end up with b squared at the end. And we end up with a plus 2ab in the middle. And this is always plus, we notice. Okay? Now, if a is negative, that means this sign is going to be negative, right? Or if b is negative, this sign will also be negative, which is what we see like over here. But this is very important. This is what we get when we expand. That's the pattern. So that, this is where we're going here today, so that if you see a trinomial, that is a 3-term expression, in this form, then you know that's a perfect square, and it has 2 identical factors. Okay, so if it's in this form, it has 2 identical factors. Now let's use one of these things. So 4x squared minus 4x plus 1. Now this is in this, it's in this format. Okay, so I have 2x all squared. I have 2 times what? 2x. Okay. I have 2 times, yeah, it's 4x, I guess, 2x. And then this one is plus 1 squared, right? So you can kind of see that we have something going on here. So 2x is my first term because that's what I squared to get this term. And 2 times 1x is going to be this middle term. So 2x times what is 2x? Well, times 1. And then 1 squared is here. And this is a minus, so this has to be a minus. And then we put a square there and we're done. Now that's not, maybe this process is not the easiest process right here for you to pick out, and you don't have to pick out this process. What you want to focus on though is the beginning term and the last term. Take the square roots of this term and the square root of this term, and then see if you can double the square roots and get this term. Okay? See if you can double the square roots and get this term, because that's what we do. The square root of a squared is a, the square root of b squared is b. So if you can double the square roots of the first and last terms, then you've got a perfect square. All right, so let's take, this is from your textbook, the Pearson Foundations and Pre-Calculus Mathematics 10 textbook here on page, section 3.8, whatever that's going to be. I don't know what page is offhand. Anyways, what this says here is that a perfect square trinomial is in this format, where the first term is the square of the first term of the binomial, like I just said. The last term is the square of the second term of the binomial. And then this middle term here is double the a times b, double these two terms. Okay, that's what we're looking for. As I mentioned before as well, it could be, you could have a negative in here, which means that there's going to be a negative inside your factors. Okay? So that's what a perfect square trinomial looks like. It's a binomial. When you multiply it by itself, you get a perfect square trinomial. All right? So a binomial times itself gives you a perfect square trinomial. And what we're going to do is we're going to be working backwards from a perfect square trinomial into factoring into the two binomials. All right, so let's do this together. Let's see how this is going to pan out, okay? So what we want to do is we want to, first of all, take any greatest common factors out, I guess, if we can. Here there's no GCF. So what I'm focusing on is this term and this term first. So this is my possible a squared, and this is my possible b squared. So what would a be then, if this is the case? A is 2x. B is going to be 3. Okay. So now this is a plus. So this is what I'm going to check. And this is how you test this, guys. You simply go, okay, if this was a perfect square trinomial, which it looks like it could be because these are perfect squares. All right, check. Now, if 2x and then plus 3, okay, that could be the factored version. Now you want to test to see if 2x times 3 times 2 gives you this term. So 2 times 2x times 3. What does that give you? That's 12x, positive 12x. Does that match with this? Yes, it's a perfect square trinomial, and here is our factored version. Okay? So, and this thought process will go pretty quick in your mind once you kind of get the hang of it. So again, you're looking for, if it's a perfect square trinomial, this will be a perfect square, and this will be a perfect square. Okay? All right, let's test the next one. 4 minus 20x plus 5x squared. Is this a perfect square, and is this a perfect square?
Yes.
Yes. What's the square root of 4?
2.
2. What's the square root of 25x squared?
5x.
5x. Very good. Now this is a minus, so if this is going to work, we're going to have a minus here. So let's check to see if this is our factored version. So again, what you want to check, because you already checked a squared and b squared, so we're going to check 2 times negative 5x. What does that give you? Negative 20x. Is that the same as what I see here? yes, you're done, this is it. Okay, check the squared as the first term, the squared is the second term, perfect squares, yep, so square root them. Do a quick 2ab to see if it matches the middle term, you're done. Okay, let's do another one here. So let's do, watch me even write this out. So you get, oh, it's supposed to be 12. Okay, so let's see if this one works. Okay, very similar to one we just did, isn't it? So is this a perfect square?
Yes.
Yeah. Okay, 3x. Is this a perfect square? Yep. 2. And this is a plus, so this should be a plus. Does that give us this polynomial? Well, we already checked the first term and the last term. So 2 times 3x times 2. That's 4 times 3x is 12x. Yes, so we're done. Okay, you getting that? You getting that? Okay. You understand what a perfect square trinomial is?
Yep.
Okay, it has two identical binomial factors. A perfect square trinomial has two identical binomial factors. So it's a binomial factor squared. All right, let's take a look at this. This is a second type of question we haven't really done much before. This looks really complicated, but it's not so bad. We are going to factor trinomials in two variables. This is not necessarily perfect square trinomials now. I just want to go over two variables, okay, for our perfect squares. So write down each of these, leave some space so we can work with this, okay? Okay, so how do we approach something like this? If we were trying to factor this trinomial, this looks quite a bit different because we have two variables now. So what you want to think about is if we can factor this trinomial, 3 terms, should factor into two binomials. Okay? This is what we've been working with, so we should have factors of two binomials that when we do the FOIL method or the distribution method, we should be able to achieve, this as our final answer when we multiply these. So the two variables looks like this. You're going to have one variable in the first term, and you're going to have a second variable in the last term. Okay? Now we still, just like we did sections ago, days ago, we still want to try and figure out what factors will multiply to these terms. So 2a squared still has to come from 2a times 2a. And 3b squared still has to come from, 3 times b times b. So this is where you're going to get, now I'm going to try this right here, 3b and b. So this still has to come from a product, this has to come from a product. Now, if you notice the FOIL part, okay, that is the outside part. That's going to give me 2ab, right? When I multiply a and b. This is going to give me 3ab. Now the question is, you see, this is where the ab in the middle term comes from. It's a mix, right? So does 2ab and 3ab, does that add up to -7 in any way? No, we got a bit of a problem there. So this is where the two variables come from. Each term carries a different variable. And then you're going to want to still do your testing, your trial and error, intuition, to see if you can get sum of products that will add up to your middle term. So what about a 6ab and a 1ab? Can I get to 7 there?
Yes.
Oh, it looks like it. Now, if I did -6ab and -1ab, do you see how that gives us -7? Now, does this multiply right here? Does this multiply to +3b squared?
Yep.
It does. It does. So using intuition, that's where our two variables come from. You have a variable in each of the terms of the binomial. And you still factor the same way. That was through intuition. Okay. If you want to do decomposition, which I'm marking your quizzes here, and some of you are not doing decomposition, by the way. So it is part of the course. You have to learn that method. So some of you are not doing that method, you're just using intuition. So on questions where I say use the decomposition method, you have to use the decomposition method. You have to show me that you know how to use the method. It doesn't have to be your favorite one, but you have to show me that you know the steps, okay? That's part of what we're learning here. So if you know a different way, that's great, but you have to learn the methods I'm teaching. So make sure on the tests and quizzes, if it says use decomposition method, that you actually do that, okay? But the decomposition method here would, again, we're going to primarily focus on the numbers. So 10 times negative 2 is negative 20. So what are the factors of negative 20 that would add up to negative 1? But negative 5 and positive 4, you see that? Adds up to negative 1. So in the decomposition method here, everything's the same. So I'm going to write 10c squared. Now I'm going to decompose this middle term using these coefficients. And because this is a CD term, I have to do negative 5CD or minus 5CD plus 4CD. See, that's where they come from. Okay? Factor by grouping. That group. So this one's going to be what? 5C. That's going to be 2C minus D. This one's going to be a, let's try plus 4 D. This is going to be 2C minus, oh wait, sorry, not 4. I need a 2. 2D. So that's going to be 2C minus D. And yes, we do have the same factor here. Oops, I didn't mean to cross that out. Oh, my computer is lagging. We have a common factor, so that's great. So you need to pull that factor out. 2C minus D. And then we're left with 5C plus 2D. Okay, so there's just another run at decomposition. Questions? All right. There's two parts to this lesson. Here's the second part. Factoring what we call a difference of squares. Have you guys heard of difference of squares before? We talked about this? Or is this the first time hearing about it? First time? Okay. Difference of squares. What is a difference of squares? Well, pretty self-explanatory. A difference means a subtraction. And squares means perfect squares. So when you see this is now a binomial, but it's a special binomial. If you have a perfect square and a perfect square, and it can be written as a subtraction, so you have one minus the other, then you have what's called a difference of squares in this form right here. In factored form, a difference of squares, let me just show you this visually. If you just kind of think about this for a bit, it might make a lot of sense. Okay, sometimes the visual is like, sometimes it makes a lot of sense for students, sometimes it doesn't. But if you think about it, if you were to write, draw a rectangle that is dimension A, right here, by dimension A, this large rectangle right here that I'm going to highlight is A squared, right? So it's A squared. Now, if I took off a B by B square, this would be B squared, right? The whole thing is A squared, this is B squared. So A squared minus B squared, if we were to draw this pictorially, you would have just this part of this. This is A squared minus B squared. Everyone see that? Now, if we separated these, okay, if we separated these, then we could rearrange this, taking this piece right here and putting it up over here. We could rearrange this into a perfect rectangle, and it would look like this one. And another way that you could show the dimensions of this rectangle would be A minus B, that's this part right here, A minus B, plus B, that's this length, times this is A minus B as well, times A minus B. And so this simplifies, the whole length simplifies to A plus B, and this width is A minus B. So when you multiply these two together, you get this part, which is actually the same as A squared minus B squared. So visually, that might make a lot of sense to you as to why that is. You don't have to think about this every time, but again, that hopefully should reinforce your belief that we should have this as the factored form, a minus b times a plus b. And so this is going to be real easy to remember how to do this. Okay? Jot down these examples. And we'll factor these together given our principle of a squared minus b squared equals a plus b times a minus b. Okay, let's start with the first one. A squared minus 16. You want to ask yourself, are these perfect squares, these two numbers? Yes. Is this a difference? Yes, it is. So this is a difference of squares. So I'm going to take this pattern right here, and I'm going to factor it. So a difference of squares does factor down to two binomials. The first terms in each binomial are the square root of the first term. So that's going to be an a here and an a there. The second terms in each of the factored form of binomials there are going to be the square root of the second term. So the square root of 16 is 4. So you put 4 there and 4 there. Now this looks like a perfect square trinomial factored version, doesn't it? Except for this fact, that we are going to put a plus here and a minus here. And I'll show you why that's important. Okay? This is the answer. This is your factored version. And the reason why it's important that one's a plus and one's a minus is because when we expand this out, what we get is this. Right? When you do the binomial expansion there, you do FOIL method, and notice that a plus and a minus cancel each other out. So there is no middle term anymore. So the plus and the minus cancel out the middle terms, and all you're left with is a squared minus 16. Okay? So it's very close to a perfect square trinomial, except instead of these being the same, they're different, they're opposite. Okay, question? Yeah?
It doesn't matter which one it is, right? Like, either could be, or like...
You mean the order of plus or
Yeah.
minus? Yeah, no, it doesn't matter. So this could be minus first and then plus in the second one. It doesn't matter. Because when you multiply two things together, it doesn't matter which order they're in. You always get the same product if you switch the order. Okay, let's keep going with this one. 25a squared minus 16b squared. Is this a perfect square?
Yeah.
Yes, it is. Is this a perfect square? Yes, it is. Okay, so our binomials are going to consist of the square root of this 25a squared, which is 5a. So that's going to go in both. The square root of 16b squared is 4b. And then separate those by a plus and a minus. And it doesn't matter which order. And if you expand that out, you'll get this original difference of squares back. All right, let's keep going. Let's keep going. Oh, this one, C. Ooh, this is tricky. It hasn't got a squared on it. It's got a 4 to the power 4. Is that a perfect square?
Yeah.
Is d to the 4th a perfect square? It is, because what you want to remember is, for perfect squares, do they have two identical factors? And d to the 4th, whoa, just disappeared on me. D to the 4th power has two identical factors of d squared. So yes, that's a perfect square. And of course 64 is as well. It's 8 squared. So this is d squared here and here. They have to be the same, the square root of that. And then this is going to be 8 and 8 plus minus done. Questions about that one? Okay, D. This one looks a little funny. It doesn't look like it's a difference. So we got a problem, right?
No.
We don't have a problem because the fact that it can be written as a difference. So if you switch those terms around, then what you're going to get is you're actually going to get 49 minus 9a squared, you see? Because this is a negative 9a squared there. So if you just flip those around, it actually turns into a difference. So yeah, so don't get fooled if there's not a minus sign in between the terms. So this one is actually a difference of squares as well. So real quickly, we have 7 and we have 3a separated by a plus and a minus. Done. Okay. Okay, any questions at all about these examples I've given you? Yep.
If you minus 3a plus 7, and then 3a plus 7.
Yeah, if you did a negative 3a plus 7 and a positive 3a plus 7, that's fine too. Yep. I just would rather not get too hung up on the negative part. Negative 3a plus 7. No. Yeah. Here's the thing. The square root of negative 9a squared, like you have to be real careful with this because nothing squared gives you a negative. Do you know what I mean? So you kind of have to forget about this negative sign in front, really. So you do this and you do this. Yeah, so it's just a little more confusing. So I would flip them around. But yes, if you did negative 3a squared on this one and then positive, or negative 3a and positive 3a, that would work out, but both have to be plus 7 and plus 7. The only problem is someone would look at that and say, hey, the square root of negative 9a squared is not negative 3a, which it isn't. Because negative 3a times negative 3a is positive 9a squared. So that's where it gets confusing. So I would rearrange those and write them like this. But yes, it's the same. Okay, this is, I think, the last example before I give you your assignment. So you have to go. Yeah, you go ahead. So the last one here, this is just a little bit more complicated in that there's other, there's a greatest common factor we'll pull out. And we're going to get down to another squared term, and so we have to factor a few times here. So let's take our GCF out, which is a 5. So I'm going to write the 5 outside. Please don't just make it disappear. It has to be written outside. It has to be factored. So it's still there. But this is going to be what? X to the 4th minus, what's 80 divided by 5? 16, isn't it? I think it's 16. 16y to the 4th. Okay? We good there? GCF? Okay. All right, now I'm looking inside here. Is this a difference of perfect squares?
Yes.
Yes, it is. Just a hint. If you have a variable that is an even number, that's a perfect square. Okay? It is. It's a perfect square. Anything even. So example, x to the 10 is x to the 5 times x to the 5, right? Because you have to add exponents. Those are the rules for exponents. So if you have x to the 200, that's x to the 100 times x to the 100. So yes, it's a perfect square. So any even exponent on a variable is a perfect square, okay? If it's divisible by 2, it's a perfect square. All right, so back over here to the question, 5. Now, I'm going to split this up into a difference of squares. The square root of x to the 4th is x squared. X squared. The square root of 16y to the 4th is 4y squared. 4y squared. I'm going to put a minus and a plus here. Actually, I'll put the plus here and the minus over here. Now, you might say, okay, good, done, move on. But this is not fully factored. Why not? Do you see anything?
Yeah, because
That would- Sorry?
It can be broken down
Okay, what can be broken down again?
to x times x and
Okay, which one can be broken down further? Or when you say broken down, which one, you mean factored, right? Which one can be factored down further? The first, the second, or the third factor? Is not what you meant? Not what you meant? Which factor can be factored further? Only one of them can be factored further. Do you see which one? The third one. Why?
Because the first one is multiplied by 5.
Okay, the first one is just a 5. This second one, it's not a perfect square trinomial. It's not a difference of squares. There's no greatest common factor. But what about this one? This is, you're right, saying the third. Why? Why can I factor this third further?
Because it's a difference of squares, number one.
It itself is a difference of squares. This is a difference of perfect squares, so we can factor this one further. So yeah, we're going to focus on that third one. So I rewrite the 5, rewrite the x squared plus 4y squared. This now can be factored into two binomials. Difference of squares. This is an x. Yep. This is an x.
Couldn't you factor the first one because it is a perfect
Yep.
square trinomial?
Yeah, you could factor this as a perfect. Well, you could factor this as a difference of squares. No, you couldn't actually. You have to take the 5 out. You mean this one? You mean this one?
below it.
You mean this one?
Yeah.
Okay, it's the same as the one I just underlined, but
Oh, yeah.
no, you can't factor this as a difference of squares because it's a sum of squares. A sum of squares, you can't factor that one. Only a difference. Yeah. So it's only a difference of squares that you can factor like this. So plus minus here. Yeah. So yeah, that's the final answer there. That's the final answer. Okay. This is real big kid math here now. Okay. Real big kid math. When you factor, check your factors again to see if there's anything further you can do with any of the factors, and then keep going as far as you can. Questions? Yep.
Are we going to be using this in calculus?
Are we going to be using this in calculus? Yes. Why we're doing it? Absolutely. Yes, you have to know how to do this for sure. Factoring is probably the most important mathematical skill in high school. Being able to factor. Probably the most important, I would say. That and knowing your times tables. Yeah. But yeah, factoring is huge. Okay, here's your assignment from 3.8. I'll make that much bigger for you.